Welcome. Thank you all for coming here in person and remote. We do appreciate the remote people. Well, this will be the final curriculum from the mathematics curriculum series this year. We will pick up again in September or October, depending on. It is my pleasure to introduce to you Professor Leahy. He will be introducing today's speaker because it is his student. Professor Leahy, you're up.
Professor Forsberg, thank you very much. So as you can see up here, Hal's going to be speaking today on neural networks. And he came to me, I think the beginning of this term, he said he wanted to do his final senior research looking at the mathematics behind machine learning. And so in particular, like the hottest area in machine learning is neural networks, and probably, neural networks in some sense are probably the hottest topic on the planet right now in some sense. So the issue with these, however, is that, the approaches I tended to see were one, either very cookbookish, these are the libraries and these are how you use some of these. On the other hand, this is still an extremely, and How's going to be able to explain this, an extremely active area of research. And so you can find lots and lots of research papers that are awfully hard to go through. But we found a very kind of what appears to be very popular mathematical introduction to neural networks on the web. And we're going to be following this throughout, that makes use or that references probably one of the most famous machine learning data sets out there, the handwritten recognition digits. And in fact, if I recall correctly, Jay Wong, and I forget when he talked, that was 3 or 4 or maybe 5 years ago, did something very similar to this using this data set as well. Now, I've listened to How a couple of times, and he's going to move quickly because he has a lot to say, and it's very interesting stuff. But I do want to encourage you, if you have questions, to feel free to ask them so that we can clarify them as we go through. This is not, like an honors exam where we're going to figure out the limits, hopefully, of your knowledge or anything like that. But if you want, I think this is such an interesting topic that if you want or you think you need some clarification, please feel free to do that. So I present to you Hal Lee speaking on using neural networks to recognize handwriting digits, which I know is his first slide, so I probably just ruined it already.
Thank you, Professor Lee. Okay. So let's get started. Today, I'm going to present how to use the neural networks to recognize the handwritten digits and to approximate the functions. The idea is that we construct the network and train the machine to learn the features of many, many different handwritten digits. And we hope that according to these features, the machine can give us a good prediction of those images. So let's start with the motivation. I think there's no difficulty for anyone to recognize the 6 digits, 504192. Even it's a little bit blurred, we can recognize this in just less than a second. This is because in each hemisphere of our brain, humans have a primary visual cortex, which is known as V1, containing 140 million neurons and tens of billions of connections between them. So let's look at the picture below. On the left side, we have the structure of a human neuron. So first we have a dendrites where we collect the information. And then we have cell body and we have axion. And at the end of axion, we have axon terminals where it connects to the next neuron. So we have 140 millions of this structure in our brain. And on the right side, so we have artificial neuron. So we're going to imitate this human neuron and to construct an artificial neuron. First, we need to input information, just like the dendrites. And then for each input, it has its corresponding weights. So we have x1, x2, x3 as inputs, and it has corresponding weights, w1, w2, and w3. And for each input, and then we're gonna pass this weighted inputs into the neuron, this neuron here, where it can be, we can consider as a cell body, and it contains a bias. And then we're gonna, after adding these biases, we're gonna send this weighted inputs to the activation function. And this activation function is inside that. We can consider as inside this axiom here. And the axiom going to return us a value. So after we evaluate this activation function, we have an output. And at the end of activation function, it connects to the next neuron. So we're going to send out this output to the next neuron. And then the next neuron going to repeat this process again. So we see the output from this neuron is just a function of weights and bias. So that implies the prediction of this from this image of this network is just a function of weights and biases. So the weights and biases are very important because it gives us how good this machine can predict. And more importantly, the key idea of machine learning here is just to learn good weights and biases so that the machine can give us a prediction as close as possible to the correct answers. So to make this idea more concrete, let's look at the simple example first. So this is a very simple network. We have only 3 layers. The first column, we're going to call it the input layer. The second column, we're going to call it the hidden layer. And the third column, we're going to call it output layer. So first, let's look at the notations. Let WJK denotes the weights from the connection for the connection from the K's neuron in the L-1 layer to the J's neuron in the L's layer. So for example, this one, W112, means the weights connects from the first neuron in the first layer, which is the hidden layer, to the second layer, to the first neuron in the second layer, which is the output layer. And the BJL denotes the J's bias in the L's layer. And the activation can be written as the activation function evaluated at the weighted inputs plus the bias. We can consider this network as approximating a simple 2-variable function, which is the x1 squared plus x2 squared over 2. So let's see, this C here denotes the cost function that measures error between this prediction here, the AL, and the correct answer. So for this machine, if it wants to approximate the 2-variable function, we need to make it to find a good weights and biases. And this is because the cost or the arrow here is just a function of the output. And we have seen before, the output is just a function of weights and biases. This implies the arrow from this network is controlled by the weights and biases. So for this specific example, we see the output layer AL is a function of weights and biases between the hidden layer and the output layer. And again, this A1, A2, and A3 is also a function of weights and biases between the input layer and the hidden layer. So we see that the cost of this network, or the error of this network, is just function of a activation function composed with another activation function here. So this is an activation function composed with another activation function, where the variables are the weights and biases in each layer. So to approximate this x1, x2, and the x1 squared plus x2 squared over 2, we need to input tens of thousands of pairs, x1, x2 pairs, and to train this machine. And we hope that this machine can find the best weights and biases that can minimize this cost function, this error here. So now you may wonder, what's the cost function and what's the activation function? So now I'm going to introduce these 2 functions. And first, I want to mention that these 2 functions I introduced here is not the only choice, and we have a better choice later. That's why we need to improve it. But I choose this 2 because this is the easy to understand. It's just our first example. So the cost function is just the mean square error. So here y of x is the correct answer. So after we decided our input, we input our x, all the information, this y has been decided. And the a is the prediction. So we just find the differences between them and square them and sum them up. And the 1/2 is just normalization constant, where n is the total number of training inputs. The sigmoid function is just a logistic function, which is 1/1 plus z to the power of 1 plus e to the power of minus z, where z is again our weighted inputs plus the bias. So if we look at the graph of this sigmoid function, this is the graph of sigmoid function. We see it's a smooth curve. That means it's differentiable everywhere. So it's a good news. So when we take the derivative, we don't need to worry about the existence of the partial derivative. Now we're already knowing the output. No, so we have this cost function. We have the activation function. Now we want to look at more complex example. So this structure here, this network is the one we're going to use to recognize the handwritten digits. First, look at this. We also have 3 layers: the input layer, the hidden layer, and output layer. First, look at this input layer. We have 784 neurons in this input layer, and on the right side we have 10 neurons. Why 784? This is because in our database, each image is a 28 by 28 pixels. So in total, that we have input all these pixels. Each pixel will have a grayscale value. So we're going to input these pixels into this neurons. And at the end, we want this network to give us a prediction. Because there are 10 digits, we just need 10 neurons. So what this network do is, forgot to mention, between them, if 15, we can choose any number we want. We can choose 30, we can choose 45. So here I just want to choose 50 because it can fit in this page. And this two ends is fixed. The number of neurons is fixed. So what this network do is we input the grayscale value in each pixels one by one. So on the top corner one, it's going to send to the first neuron. Again, the second one going to send to the second neuron. Just one by one, row by row. We're going to input all the grayscale value into this input layer. And then we're going to calculate the weighted inputs, the Z, and the activation. At the activation, and then we're gonna, at the end, we're gonna get a final output. And how do we know the predictions? So at the output, we're gonna return so each neuron is gonna give us a value between 0 and 1. We're gonna find the maximum probability. For example, this 7, if this 7 has a number 0.9, and it's a maximum value among all of those 10s. So we say this neuron give us the prediction, which is this number is 10. So now we know the output. Now we know in the output, we compare it with the correct answer, which is the correct answer is the y of x, right? So this is a function of output, which is a composition, which is activation composed with another activation function. So here we have 784 weighted inputs, because between these two layers, we have 784 weighted inputs. Between these two layers, we have a 50. So it's activation composed with another activation function. We're going to find the difference between them and square them. And that's the error for one image. And in our training data, we have 50,000 training data. So we're going to add all these errors together. So we're going to add from the first image to 50,000, and we times 1/2 times 50,000. That's the cost function. So now we find the cost function here. Now what we need, we just need to find the weights and biases to minimize this cost function. So if I just learned calculus 2, my first choice would be just take the first derivative, set equal to 0, and solve for the weights and biases, and do the second derivative test to find for the minimum or maximum. But unfortunately, that's not going to work because, or I should say, theoretically it works, but the cost is just too high. The computation is too complicated and it's going to take too long to compute those derivatives. And it's not an efficient way. So we must find a numerical way to find this minimum of this cost quickly. So now that's how the gradient descent is going to help us. Gradient descent technique can help us. So let's look at the definition of the gradient. That R is scalar field maps from Rn to R. The gradient of G at X, so X is our point, is denoted like this and defined by the partial derivative of G with respect to X1 evaluated at X and partial derivative of G with respect to X2 evaluated at X and so on. So here, I want to mention that the X is just in general we call it X, but in our neural networks, our X is just the vector of weights and biases. Now, so if we let V be a unit vector, then by the definition, the directional derivative of G at X in the direction of V is defined by the V dotted with the gradient of G evaluated at X. One important theorem about gradient is that the gradient of F points in the direction of the maximum rate of the increase of the scalar field F. Here's a quick proof. By the definition of dot product here, we can write this dot product is equal to the magnitude of gradient F times the magnitude of V times cosine theta. And because V is a unit vector, so this is 1. So it becomes the magnitude of gradient F times cosine theta. And theta is the angle between the gradient F and V. Since cosine theta is between -1 and 1, so we know when theta is equal to 0, cosine theta is equal to 1. So we have our maximum value. And because the directional derivative tells us how fast this scalar field is changing along V in the direction of V at this point X, that tells us the quickest way or the quickest path to find the minimum is just follow where the gradient is pointing. And this is very important for machine learning because as a human, we learn the lesson from our mistakes, right? After many mistakes, we know which way we should go next to avoid those mistakes. but the machine doesn't. So we need to tell the machine which way is the best way to go. That's how the gradient is going to help the machine to learn to minimize the error. Now here's the gradient. Here's the gradient descent technique. So here's the algorithm we're going to use. So let R again be the scalar function mapped from Rn to R, and let x naught denotes the initial point, and eta be the constant, which is greater than 0. So later we could call this eta, we call it the learning rate. So the algorithm is the following 4 steps. First, we evaluate G. First, we evaluate G at the initial point, like for example here, and then we determine the direction from F that results in the fastest decrease in the value of G. So we know this direction is given by the gradient. And then we move certain amount in this direction, and that certain amount is controlled by the learning rate, which is the eta. And we're gonna get a new value. And we set this value as a new starting point. So we repeat step 1 through 3 with x now replaced by x1. So this equation generalizes the first 3 steps. x1 is equal to x naught minus eta times the gradient of G value x naught. I will just go to repeat this doing many times until we find a local minimum there. So to make this ideal work, but we're going to do something a little bit different. This is because we have 50,000 images. If we find all the gradients of them, it's going to take too long. So the idea is that we're just going to we want to estimate the gradient of C by just computing the gradient of Cx for a small sample of random chosen training inputs. So first, we're going to label this training inputs x1, x2, and xn, and refer them as a mini batch. So usually inside each mini batch, we have 10 images. So if the sample size m is large enough, we expected that this average value of this average value, so this is the average value of the gradient C xj is going to equal to the average value of all those gradients, which is our actual gradients. So hope this is going to be about equal to this actual value. So if we apply the stochastic gradient descent, the new weights and biases are given by the formula WK1 is equal to WK0, which is our O point minus the eta over n, where we take the average of the sum of those gradient. And similarly for the biases. So look back to this, the idea is still the same. We start a new point, we follow the gradient, move a little bit, and we find a new point and keep doing this. So we just want to take the average, and this stochastic gradient descent is going to help us and speed up the process a lot. So it's a really useful technique to speed up the calculation. Now we just need to find a gradient, and we're almost done. But the problem is, we go back to this simple example here. We have three layers, and if we just use the chain rule to take the partial derivative of C with respect to the weights in the first layer, for example, that first weights, we have seen that this AL is an activation composed with another activation. So by the chain rule, if we expand this, we can have the formula like this. But in general, for more complex example, for more layers, by the chain rule, the partial derivative of C with respect to the weights is going to be written in this formula like this. Remember our picture, this neural network? Between these two layers, we have 784 times 50 weights. Between these two layers, we have 150. And don't forget, we still have biases to calculate. So the cost is really high. So if we just calculate all the and the partial derivatives one by one, the time is going to take too long to calculate. So that's how the back propagation changes the game. So let's look at the back propagation. First, we start by the definition of arrow. That arrow of J's neuron in the layer L is defined by delta JL, which is equal to the partial derivative of C with respect to ZJL, where ZJ again is our weighted inputs plus the bias. So the theorem says the partial derivative of the cost with respect to any weights and biases can be found through the following 4 equations. So these 4 equations I have already written on the blackboard and the cap table. If people want to switch to there, you can see it. Also, you can also see it from here. So why these 4 equations help us? So let's look at equation 1. Equation 1 tells us the arrow in the last layer. So this capital L always denotes the last layer. So the arrow in the last layer is the partial derivative of C with respect to AJL, which is output in last layer, times the sigma prime divided by ZJL. And the equation 2 tells us if we know this delta L plus 1, we can write delta L in terms of the delta, the arrow in the last layer here. And equation 3 just tells us the gradient of the biases is just the arrow in that layer. And the gradient of the weights is just the arrow times the activation in the previous layer. So, so instead of computing many partial derivatives, we just need to compute, for the equation here, we just need to compute the partial derivative of the cost function with respect to the output layer and the sigma prime. And the rest of computation is just multiplication and summation. And these 4 equations really help us to find the gradient quickly. Now we just need to prove this 4 equation to show that it really works. So let's look at equation 1. So by the definition of the arrow, we have delta JL, which is equal to the partial derivative of C with respect to ZJL. So this is the arrow in the last layer. And since the delta, since the output AJL is the sigmoid function divided by ZJL, so by the chain rule, we have an expression like this. So by the chain rule, that's the chain rule of the sigma prime, sigma divided by ZJL. If we look at the last part here, this part, this by the definition, this gets the sigma prime divided by ZJL. So we just substitute this into that, and that's our equation 1 written here. That's our equation 1. For equation 2, first we write the formula. We write the arrow formula. So we take the partial derivative of C with respect to ZKL plus 1. So this one here. So by the chain rule, we should have this expression here. And nothing magic happens here because you see the denominator and numerator, it cancels out. It's just an expression. It's just the definition of our arrow formula. So we rewrite this. And if we look at the first part, which is this one here, this is the definition of arrow of K in the L plus 1's layer. So we just replace that with this arrow delta K L plus 1. So we rewrite this arrow formula L in terms of the arrow in the layer L plus 1. And note that our Z, which is how we define it, the weighted inputs plus the biases, and the input is the activation function, the divided by ZJL. So if we take the differentiating with respect to ZJL, we have so B is just a constant, it's 0. And the W doesn't contain any ZJL. So it's just going to be a constant attached here. And we have sigma prime ZJL. Now we just substitute this back to this equation here. We substitute this back to this. We got our fundamental equation 2, which is written here. Now for equation 3, again, by the definition of Z, which is weighted inputs plus the biases, and we just take the derivative with respect to BJL. So the bias, we got W and A doesn't contain any bias, so it's 0, and the BJL becomes 1. Now we multiply this partial derivative to both sides of the arrow formula. So this is arrow formula, and the 1 multiply this delta, JL is just still delta JL. And on the right side, we see the denominator and numerator cancels out. So that's the partial derivative of C with respect to BJL. And that's fundamental equation 3. Similarly, for the equation 4, we do the same trick. we take the derivative of z with respect to wjkl. Because b is just a constant, it's 0, and the only thing left is the akl minus 1. We multiply this equation to both sides of the arrow formula, and we have this delta JL times the activation in the last layer. And on the right side again, the denominator and numerator cancels out. That's our gradient of the weights. So, and this is the fundamental equation for it. Okay, so now we see the back propagation really help us. So we have proved this. That means we have proved this. That means this back propagation really help us to find the gradient quickly. And the gradient descent technique can help us to find the minimum of this cost function really quick. So that means our idea really works. We have a quick way to find the gradient. Now we have a quick way to find the minimum. Now we just need to implement this network by using these ideas. But before that, I just want to take you guys to look at our data, our database. So this website is where we download our data. So this is created by these people, and they collect so many handwritten digits images. And here you can download those files. And this is a list like for other people's experiment. We see this is different classifiers. We have a test error rate. And this is the neural networks. People using neural networks. We have two. This one is the 2-layer neural networks with 300 hidden units. He also used the mean square error, and he has like a 4.8 error rate. And this is like done by like 1998, so a long time ago.
What does 4.8 error rate mean? That's the percentage?
Yes.
So about 5% are incorrectly classified.
Yes, that means the correct accuracy is 95.3. Yeah. So let's go back to the slides. And inside that data, so for each image, as we showed before, it's going to look like this. So there's no, this is just a simpler one. We have a 28 by 28 matrix here. So each value, each pixel has a grayscale value. So for example, this one, most of the part going to be 0. And some part here, like here, we have a grayscale value 1, we have 0.7, 0.4. And I also want to take you guys to look at the data structure. So I use the Jupyter notebook. So we export the data. First, we have the data loader, the MNIST data loader, where let me zoom in a little bit. Yeah. So here we open our files. We name it training data, validation data, and test data. And here in this notebook, I print this data. So for this code, so this is the test data. So for the for each list is one image, and each number here is the correct answer. So that's the answer. For example, this image is going to be 7, and this image is going to be 2. Of course, the machine never going to know the correct answer. You need to predict it. And if I print the first image in the test data, which can be looked like this. We have seen before. It's just not so zeros for most of the part, grayscale value, and we have some grayscale value here, like this. So yeah, there are 784 grayscale value in this matrix. Let's look back. So now we just need to implement the network. What we do first, we give a mini batch of n examples. So for each mini batch, we have like about 10 images. And first we're going to input for each image, for each training input X, for each image, we're going to first, as we see before, we input those grayscale value one by one in the input layer, and we compute, we feed forward. So we can compute the weighted inputs in each layer and the activation in each layer, and yeah, from layer 2 to the last layer. So look, after computing this, we're gonna compute the output error, which is according to this fundamental equation 1, we can compute the output error. So compute the output error according to this equation, and we back propagate the error. That's why we call this back propagation, because once we know the error in the last layer, according to the equation 2, we can compute the error in the L-1 layer and the L-1 and L-2 layer. So we can compute the error in each layer. And now, after computing the error, according to equations 3 and 4, we'll be able to compute the gradient of the biases and the gradient of the weights. And then we store this weights and biases. I'll put it there, and we go to the next image. We do this process again. We have another bunch of gradient and biases. After we finish that mini batch, so after we finish that 10 images, we update our weights and biases. So for each layer, we're gonna update the weights according to our stochastic gradient descent here. And this is the gradient of the weights, which is here, the fundamental equation 4. And that's the gradient of the biases, which is given by the fundamental equation 3. So let's look at the code. First, this code is not it's not my code, and it's provided by the author. So I just want to introduce this code slightly. Since I'm not a CS major, but I just want to mention some important part of this code. So yeah, it's big enough. So first, let's look at this 2 line. First, we generate the initial weights and biases from a standard normal distribution. So we have our initial weights and biases, and we want to minimize this. Find a better one to replace those initial weights and biases. And we feed forward. That's our equation, and we have stochastic gradient descent SGD. Here, first we shuffle the training data, and for each mini batch, and then we generate the mini batch first. And for each mini batch, we're gonna call this function update mini batch, self-update mini batch. And what's inside this? We update the weights and biases according to the equation we have to see. These 2 equations here. Yeah. So these 2 equations update the weights and biases. And where the gradients comes from? Before we update, we're going to call this function self.prop. So inside this function, we have our update, or we have our gradient. So in the back propagation function, we first feed forward, and we feed backward. This lines here, we find this is the error in the last layer, fundamental equation 1. And we know the error in the last layer, and we can compute we calculate the gradient of biases and the gradient of the weights according to the fundamental equation 3 and 4. And inside this loop, we find the error in each layer. And according to these 2 equations, we can find the gradient of weights and biases in each layer. So that's the definition of that's the fundamental equation 3. And this is fundamental equation 4, which is the error times the activation in the last layer. And here is the how they found the output. So in the output, for the output, we got this function argmax gonna return the indices of the maximum probability. So here we're gonna compare that indices, which is his prediction, with the correct answer. If it's equal, we're gonna count it. And here, yeah, we're gonna print it. So we're gonna count the correct. So here is total number of successful and over the total number of training test inputs. And here is just the definition of sigmoid function. And here is the definition of a sigmoid prime. So let's just run this code. Now, this line imports the data. And this line, we generate our network. The first, as we say, 784 neurons. The second number, 30, I use the 30, hidden area, I use the 30 neurons. For the output layer, we have no choice, we have to use 10 neurons. And 30 here means I run 30 epochs, so 30 iterations. And 10 is the mini batch, the size of mini batch. So for each mini batch, we have 10 images. 0.5 is the learning rate. So it's gonna take some time. So let's go back to our slides. So what is network actually learning? As we said before, the network wants to learn good weights and biases, so it can minimize this cost function. So I was wondering, can I just change this code a little bit to plot this weights and biases to see how it changes after each epoch? So I modified his code a little bit. So here, this 30 still the 30 epochs, mini batch of size 10 and 3.0 learning rate. This 10 means I'm gonna, because the weights between the first neuron connects to between the first layer connects to the hidden layer, there's gonna be a 30 weight, so 30 weights there. So I'm not gonna plot 30 of them, I'm just gonna choose random 10 and make a plot. Here, 0 means I choose the 0th neuron in the input layer, and 29 means I choose the 29th neuron in the hidden layer. Similarly for the biases, I just randomly plot 10 biases, because this graph cannot contain 30, it's gonna be too messy. So just plot 10 of them. This one looks interesting because the weights didn't change at all. This is because I said this image is from the 0th neuron. You remember the 0th neuron is on the top corner one. On the top corner, there's no grayscale value, and nobody usually writes a letter in that way, like put a grayscale value there. So the weight's not going to change at all. So after each epoch, it's just a string, it doesn't change. But for other weights, for example, the 29th neuron, the weights changes like this, and that's the biases. It changes like this, and this is the output biases like this. So that shows that this machine is really trying to learn some good weights and biases to minimize the cost. Now, if we go back to, I hope finish the. Let me see. Yeah, still learning. It's like 93. I hope we have a better accuracy later, but we see now we only have a 93% accuracy. So that's not good enough, right? We wish to improve our network to have a better accuracy. And another reason is that we want to improve our network because we have some problems we have for our original code. So we need to solve some problems here. The first problem is the learning slowdown. If we look at the red curve is the sigmoid prime function. That shows if we have if the absolute value of z is large, at these two ends, the sigma prime z is about equal to 0. And if you look at our fundamental equation 1, we have a sigma prime z here. That means if this is about equal to 0, this arrow is about equal to 0. The arrow in the previous layer is also going to be equal to 0. The gradient is 0. The gradient of weights and biases is about equal to 0. The machine stopped learning. That's the bad news. So one of the solutions is we change the cost function. So we introduce the cross entropy cost function, which can be written in this way. So if we take the derivative with respect to the weights and biases, we see we don't have that sigma prime there anymore. And the good news is, if this difference, which is the correct answer, the prediction and the correct answer, if this difference, the arrow is large, the larger the gradient is, and the faster it will learn. So that's exactly what we want. The second problem is the weight initialization. So remember in our first code, our weights and biases that comes from a standard normal distribution. Let's focus on the first neuron in the hidden layer and ignore the rest of the network. So we just look at one neurons. For simplicity, we suppose we have 1,000 inputs and half of them going to set to 1, and the rest of them going to set to equal to 0. So first, let's suppose the weights and biases comes from the standard normal distribution. So the weighted sum going to be this, because half of them is set to 0. So we're adding 500 Wj plus B, because W and B comes from a standard normal distribution. So Z should also have a normal distribution with mean 0 and the variance 501. So the standard deviation is 22.4. That shows it's very likely we're going to get a large value of absolute value of Z. So that means if we have a large value of Z, the sigma prime Z is going to be equal to 0. We go back to our problem again, the learning still young. So the solution is pretty straightforward. We just need to reduce the variance. So suppose we have n inputs. What we need to do is we just generate the weights from the normal distribution 0 and 1 over n. Because the biases, so for all these inputs, for all these weights, we just have one biases, adding 1 here. So this one doesn't really matter. So we just need to, so the biases still comes from the standard normal distribution. So in this case, in this specific case here, Z gonna have a follows the normal distribution with mean 0 and variance 500 over 1000 here plus 1. And so the standard deviation is just 1.22. And this is a graph. I plot these two distributions together. So the orange one is the old one. So we see the variance is really large. So it's really likely to get some really big values. And for this one, we see the variance is really small. So we're going to get some small value. If we have small value of Z, where sigma prime is going to be B, and the gradient going to be B, we're going to nerve faster, much more faster. So let's look at some problems. So our idea is that we want our idea not only work for this specific network, this 3 layers, because we want this network for more deeper and even more complex network. So for example, have more layers. But if we adding more layers, there's some problems we're gonna have. So if we look at this graph here, this is the speed of learning for 4 hidden layers. The green line is the hidden layer 4. We see the speed here is much faster than the hidden layer 3, and hidden layer 3 is much faster than hidden layer 2, and hidden layer 2 is much faster than hidden layer 1. So the gradient tends to get smaller as we move backward through the hidden layers. This means that neurons in the earliest layer are much more slowly than the neurons in the later layers. So this phenomenon is, they call it the managed gradient problem. To see this way, let's look at this simple path. So we have 4 hidden layers, 1, 2, 3, 4, and we just look at one path. So we ignore other parts. So if we take the derivative of C with respect to the B1, the bias in the first layer, it's going to be look like this. So let's suppose we still have the weights from the standard normal distribution. That means we have 95% chance the absolute value of W is going to be less than 2. Because the maximum of the sigma prime, Zj, divided by Zj is going to be 0.25. So that means we have 95% chance that the absolute value of Wj times sigma prime Zj is going to be less than 1 over 2. And we have 3 of them. So we raise to the cube. We see the gradient of bias in the first layer is going to be less than 1 over 8. So it's very likely that the gradient in the first layer tends to be very small and causing the neural network really hard to be trained. And of course, more complex the network is, the more serious the problem is. So if we have more layers, this problem is more serious. So there is solution. Good news is we have a solution. So the solution is, instead of using the sigmoid function, we change our activation function to the rectifying function. So the rectifying function is defined as the maximum value between 0 and z. So it's the max of 0 between the 0 and the weighted inputs plus the bias. And this is a graph of the rectifying function. You see, if z is less than 0, the function is f of z is going to be 0. So the whole network is going to stop learning at all. So we just need to increase the weights. And if I have more weights, if we increase the weights, this rectifying function the output and won't affect our learning rate because the derivative is a constant. And so we don't have such a learning slowdown problem anymore. And another advantage is that the computation is more efficient because in our rectifying function, we only have a comparison, we compare z with 0. We only have addition there, and we only have a multiplication. But so remember our sigmoid function, which is 1 over 1 plus z to the power e to the power of minus c. We have divisions, we have exponential. So this computation is much more efficient. And of course, we have a potential problem that is it's not differentiable at this point. But however, it's differentiable everywhere else. So we can just choose the value of the derivative as 0 to be arbitrary, to choose to be like 0 or 1. So now we have improved our code. So this is our improved code. Also, again, this code is also provided by the author. Yeah. So this is the improved code. I just want to, I think the code 1 is finished calculating. Let's look at it. So that's the results from the code 1, our original code. I think the highest accuracy we got here is 93.94. Yes. Yeah, 93, almost like 94%. So let's see how, after you improve it, I ran this yesterday. So, because it's gonna take some time to learn. So all these parameters still the same. So you see, we still have 30 and 10 and 0.5 learning rate. I think the highest accuracy I got yesterday is 96.25. I think it's here, yeah. Yeah, 96.43. Yeah, it's a little bit improved, like 2.5%. Yeah, it's a little bit better. So now let's go back to our the first example, our big picture. Remember, we have a simple function x1 squared, which I written here, x1 squared plus x2 squared over 2. So now we have already successfully built a machine that if we throw the inputs to this machine and it returns an approximation. So I was wondering, can we just build a simple network that can approximate that simple function there, x1 squared plus x2 squared over 2. So I modified his code a little bit. So most of the code still from the author, I just modified a little bit to approximate that simple function. So where I make changes here. So in our network, it returns a value x. And where is the prediction? I'm going to compare the value with the correct answer. If the absolute value of the arrow is less than 0.01. So this is the threshold I choose. If it is less than this value, I'm going to say it has a right prediction. Just count that. And similarly, I'm going to return the total number of successful over the total number of training inputs. And yeah, here I choose, so we have 2 inputs for that function, x1, x2, 2 inputs. We only need 1 output. And I choose 15 hidden neurons. So I choose, we have 30 epochs, 10 mini batch of size 10, and 10.0 learning rate. See, we're starting at a really bad point. We only have 34.18 accuracy. And it turns out it's really start learning. So I think the highest is 95.9. So it's 96%. So that means you really understand that function, x1 squared plus x2 squared and over 2. And he can give us 96% accuracy. So for the handwritten digits, still the same. We just have a more complex function to approximate, but the idea is still the same. So as long as we have enough inputs to train, the machine can give us a good weights and biases and to approximate the function as close as possible. And I found this theorem. So they actually have a theorem to talk about this. I found this theorem on the book, but I haven't had the time to look at this too much, and I haven't had a chance to prove it. So I just want to say, I think it's kind of important. I just want to state it here. So it's the universal approximation theorem. It says if g of x is a continuous function and defining a compact set S, so it's closed and bounded, which is a subset of RL. For any epsilon greater than 0, so that's the arrow we choose, the threshold. So in this case, we choose 0.01. If then there is a 2-layer networks with k hidden nodes. So k hidden neurons. So this k is a function of the arrow I choose. So depends on this arrow here. And if we have output g hat of x, the absolute value between of their differences is going to be less than this arrow for all x in S. So that's the universal approximation theory. Now we can look further. So I found this chat of different types of neural networks. So this is the website. It gives us a really complete chat of the different types of neuron. We have so many other types we see. We have so many other neural networks we can learn. So we're just in the beginning. We're here. Let's feed forward. We have so many other types. Can do other tasks. For example, like image recognition, voice recognition, such and so on. But here I want to mention that the deep convolutional neural network, because in the textbook, the author also introduced this idea. And I think it's kind of important. It's also a hot topic right now. And I just want to show that. So the convolutional neural networks. So instead of the differences, instead of we input the image, the grayscale value in one column, here for the convolutional neural network, we're just going to input the window in slides around the page, just pixel by pixel. So we're just going to input this matrix here. And then the data is passed to the convolutional layers, and that form a formula. And from the terms of image recognition, the first layer detects the gradients, and the second the line, and third the shapes, and so on. And then to the scale of the particular objects. So here is the code for the deep learning. It's also provided by the author, but I just want to show that how powerful this deep learning can be, how good is accuracy. Remember our first, the original code, we have 94% accuracy. And after we improve it, we have 96, I think, yeah. 96.5%. Let me zoom in a little bit. And this is our deep learning code. And I ran this yesterday. The highest accuracy we got is 99.14. That's a huge improvement. This one is how powerful this network is. So we see we're just in the surface. We're just in the first layer. We're just in the feed forward. And there's so much neural networks we can learn. And we have so many we can improve. So this is just the beginning. And I'm really looking forward to explore more on machine learning in the future. And here's the references. Thank you.
Thank you very much. Are there any questions for Hal?
Well, I was going to say I was disappointed because you're talking about like 99.14% accuracy, but there's actually a great image in this data set, which has like 60,000 handwritten digits. There's a great image that says, here are some of the ones that nobody can classify. And you look at it and you say, I, as a human being, cannot classify this correctly. That's how badly it is. So you will never get absolutely perfect, is what I understand. Actually, my more technical one is when you did the approximation of x squared plus y squared over 2, did you use your improved network or did you use the original baseline?
I used the original one.
The original baseline, okay.
Yeah, I think because that function is simple enough, we just use the original one, it can give us the 94% accuracy. I think if we use the improved one, we have much higher accuracy. Yeah.
Thank you. Any other questions in person or remote?
Do I need to check the chat in the?
I've been checking.
Okay.
All right, seeing none, let's have one more round of applause for Hal. And I wish everyone a wonderful summer.